In this lecture, we are going to take a look at the sequential criterion for functional limits. So if you recall from the introductory video that we did for section 4.2, we talked about how thinking about the limit of a function can be related to looking at limits of a sequence of outputs along some sequence of inputs. And so we've now spent some time with the epsilon delta definition of a limit, which is what you should be familiar with from when you took calculus. But now we're going to take a look at how that definition is actually equivalent to sequences, and then we'll have an alternative way for thinking about limits of functions in a context that's more familiar for us in this course. So the sequential criterion for functional limits, I'll write it here again, is that the limit as x goes to c of f of x equals L, if and only if, no matter what sequence you pick, with xn not equal to c itself, meaning you have a path of approach toward c. If you know that xn converges to c, then f of xn should go to L. So xn is playing the role of a sequence of inputs going towards c, and then f of xn is going to be our corresponding sequence of outputs, and we want to see that that goes toward L. The fact that we are talking about for any sequence of this form tells us that we're requiring the limit must be the same along any path of approach. When I say path of approach, I'm really just referring to the sequence of inputs that we pick that are going towards C. So we're going to prove this result in this video. And to do so, let's just remember what our picture looks like when we're talking about the epsilon delta definition. So remember that said that I could specify any epsilon neighborhood of my function, of my limit L, and I should be able to come up with a delta neighborhood that will put all of the inputs in that delta neighborhood inside that epsilon band. So here, this is L plus epsilon. Down here, we have L minus epsilon. If you come over, you can see sort of the cutoff for what it takes to be inside this band. And then as long as you pick a neighborhood that's within that range, you've got an acceptable delta value. So I could pick, say, this. Okay, so this is our epsilon band. So I could reconceptualize the limit of the function. I could take this picture and I could try to think of it in terms of sequences instead. It would have to be such that no matter what path of approach of inputs I select that go towards C, so say something like this could be my sequence going towards C, I should find that my output sequence, so the values that are associated with each of these x values that I've selected in my sequence, they should be approaching L as a sequence. So, like this value here would be f of x1. This value is f of x2. Here's f of x3. And just to label some of these points, we've got x1, x2, x3. Now, this needs to be true for any sequence, so I could pick a different sequence. I could say, let's look at my values. Let's say I picked a sequence coming in from this way. Then I would need to see that the inputs associated with that one produce outputs that are also approaching my value L. And this needs to work also for oscillating sequences if I'm coming in on the left or I'm coming in on the right. So in order to prove the forward direction, we get to assume that we have the epsilon delta picture. For any epsilon that we want, we can always get this delta neighborhood. And we want to prove that if we have an input sequence, there's a way to chop the tail of the output sequence such that it's within L of our band. So let's write down what we want to show down here. So again, we want to prove if the limit as x goes to c of f of x is L, then for all xn as a sequence within A, with xn not c, just meaning we're approaching c and not right at the point, if xn goes to c, then f of xn goes to L. And so our focus when we're trying to prove this should be on the ultimate conclusion that we're looking to make. We are trying to prove that a sequence of outputs converges to L, which means in order to do this, we're going to be relying on the definition of sequence convergence. So recall that if I knew, so we know xn goes to c, and what that tells us is that given any number greater than 0, I have to be able to chop my tail such that for all little n greater than or equal to that capital N, the distance between xn minus c should be less than whatever that box is. And we are trying to show a similar statement, but with f of xn playing the role of our sequence. So here ultimately we want to show, here I'll write it, we know that for all epsilon greater than 0, we need to show that there exists a capital N in the natural numbers, such that for all little n greater than or equal to capital N, we want the difference between f of xn minus L in absolute value to be less than epsilon. So our whole goal is going to be to figure out how do we chop our tail so that f of xn is in our epsilon band of L. So let's write that down. Goal. How do we chop the tail so that f of xn is in the epsilon band of L? Now we already have a picture that we drew, but I'm going to redraw it here so we can take a look at it again. I've got some arbitrary function, and my claim is that the limit as x goes to c, I already know is going to be equal to L. I'm assuming that. And I want to try to figure out how, given any arbitrary input sequence, how do I guarantee that its outputs are in my epsilon neighborhood? So I'm going to draw the epsilon neighborhood that I have. And right now we know that there's a way to choose a delta to guarantee that we're in that range. So right now, I know, for example, that this delta neighborhood exists. And I know that for that delta neighborhood, any x that I pick in here is going to have to end up here on my graph. What I'm going to do now is I'm going to introduce an arbitrary sequence of inputs that are going toward C. So like this, for example. And I need to figure out, how do I choose capital N to guarantee that my corresponding output values along my sequence are inside this yellow epsilon neighborhood? Well, notice that what we're given is that the moment that we select a value from inside our delta neighborhood, we have to be guaranteed that the outputs associated with those values are in our epsilon band. So notice here that if my sequence, once my sequence enters the delta neighborhood, the outputs are going to have to be in the epsilon neighborhood. So summarizing what we just said here, we know that when xn as an input is in our delta neighborhood of C, f of xn has to be in our epsilon neighborhood of L. That's just using the definition, using the epsilon delta definition of a limit. This has to be true for any x in the delta neighborhood. So in particular, it can be true for any sequence value that we select from the delta neighborhood. So the key is we are going to choose a capital N so that xn is in the delta neighborhood for all n greater than or equal to capital N. Then applying the epsilon delta definition, or applying the fact, applying the epsilon delta definition, f of xn will have to be in our epsilon neighborhood. So let's try to write this proof. So this is the proof of the forward direction, and in this direction I am assuming that the limit as x goes to C of f of x is L. In other words, I'm assuming that for any epsilon I specify, I can get a delta neighborhood such that any input from that neighborhood will end up in the epsilon band of L. Once I have introduced that assumption, I need to go back up here and pay attention to the structure of the claim that I am making. So I have already introduced my assumption here. Now I need to properly introduce what it takes to prove the structure of my conclusion. So I'm going to need to introduce an arbitrary sequence in A with xn not equal to C, and assume that that xn converges to C. Then I'm going to use the definition of sequence convergence to prove that f of xn goes to L. So first things first here, we are going to say, let xn contained in A with xn not equal to C. And we're going to assume that the xn we're working with converges. Now, the rest of our proof is devoted to showing the definition of convergence for f of xn going to L, which means we need to let epsilon be greater than 0. Our next goal is to find where we chop our tail so that the outputs are in the epsilon band. In order to do that, remember we need to know where the delta neighborhood is. So by definition of the limit as x going to c of f of x equals L, there has to exist a delta greater than 0 such that for all x in A, if 0 is less than xn minus c, which is less than delta, then, oops, this is no n here. We're just saying any x in our domain. Then when I plug that x in, f of x has to be within epsilon of L. Remember what our goal again here is. We need to chop our tail, capital N, and make the output sequence in our epsilon neighborhood. We said that relies on guaranteeing that the tail of the inputs have entered this neighborhood here, the delta neighborhood. So since xn converges to c and delta is a positive real number, that's kind of like our box in this case, there has to exist a capital N in the natural numbers such that for all n greater than or equal to capital N, xn minus c is less than delta. Note, we assumed that xn is not equal to c, so we really have this strictly greater than 0 distance being less than delta. Now notice we just made this statement that if we have a number within the delta neighborhood of C, then we can guarantee a statement about its outputs. So then we can say, so for this capital N, we know then that for all n greater than or equal to capital N, f of xn minus L has to be less than epsilon. Because here it's like we're saying, all right, pick any x you want as long as it satisfies the delta restriction, then its function output is going to satisfy the epsilon restriction. And so for us, we are using specifically values in our sequence. And because they're in the delta neighborhood and they're also in A, we get to say something about f of xn. Notice that what we've just written out here in this last sentence is exactly the definition of the output sequence converging to L. And so we've proven that given any convergent sequence of inputs going toward C, the outputs are going to have to go toward L, just using the epsilon delta definition. To prove the backwards direction of this claim, it's going to be logically easier to prove the contrapositive, because then I get to prove the existence of a sequence rather than trying to prove a for all statement. So we will prove the backwards direction by contrapositive. So we're going to prove that if the limit as x goes to c of f of x is not equal to L, then there has to exist some sequence contained in A with xn not c, so we're saying there's a path of approach other than at c itself, such that these inputs are going to go to c, but the outputs are not going to converge to L. So there are a couple things that we need to make sure we're clear on here. First of all, we want to make sure we understand what it means for f of xn not to converge to L. That is the negation of sequence convergence. So here we're trying to say that there's going to be some epsilon neighborhood such that no matter where we chop our tail, there's always going to be some outlier in the tail such that f of xn minus L is greater than or equal to epsilon. So again, this piece right here is we're saying there's an outlier in the tail of f of xn. Now, I'm going to draw us a sample picture. Before I do that, let's just make sure also that we understand what this definition of the limit not being L is. I'm going to write that out. So this means that there exists an epsilon band such that no matter how I try to pick my delta greater than 0, there's always going to be an x in A, such that when I take a look at the delta neighborhood, I know that x is going to be in that delta neighborhood of C, but f of x is going to be an outlier of my epsilon band. So here, my statement that's saying I have an outlier is this highlighted statement. Okay, I'm going to draw a picture of an example of a function that does not have a limit equal to L. And we're going to use that picture to think about how we might construct a sequence of outliers such that we have these inputs going to C, but the outputs are all going to be too far away from L. So let's get our picture. So say this is my C value. I'm going to do just a classic jump here. So here's my function, and maybe we were trying to hope that maybe the limit L was right here. Now in this picture we can see that the limit as x goes to C is not equal to L, which is the assumption that we are making in general when proving the contrapositive of the backwards direction. And what that tells me is that I get this epsilon neighborhood such that no matter what delta I try to pick, so maybe I put delta, maybe here's my delta neighborhood, but this has to work for any delta. So in particular, even as my delta neighborhood gets smaller and smaller, I should always be able to find a number in that neighborhood that is going to be have an output associated with it that's not in my band. And what we see is that it's this left branch of the function that's causing problems. So if I chose an x here, for example, then f of x would not be in the band. It's an outlier, in other words. So I want to be clever about how I can construct. So I want to construct xn such that xn is going to get closer and closer to c, and every xn is an outlier, or every f of xn, I guess, is an outlier. So this is that classic example where I know that something is true for all delta, or in this case, I mean, before we've done for all epsilon, and so then we choose this sequence of descending values of epsilon, and we're clever. So I could say, you know, for my first value of delta, I know no delta neighborhood is going to work in the sense that I can always collect some kind of outlier from any delta neighborhood. So I could pick, say, this could be my x1. Then what we're going to do is we're going to take and we're going to shrink our delta neighborhood, and we get another outlier. This one, this x that I've already picked, could be my x2. And we're just going to keep shrinking. So what I'm sort of doing here is I'm saying fix delta 1 equal to the number 1. Let x1 be the outlier. For delta 1. So in other words, I'm saying x1 is the value in my delta 1 neighborhood of C, but f of x1 is not in the epsilon band of L. I also need to be a little bit careful here that not only am I picking an x1 in the neighborhood, I don't want x1 to be equal to c, because remember, I'm constructing a path of approach that is not equal to c itself. Then once I get the first value like that, I then shrink my delta value and I say, well, I know that no delta neighborhood works, so if I shrink to a half, I could let x2 not equal to c be the outlier for delta 2. And what I would be saying here is that x2 is in my delta 2 neighborhood of C, x2 not equal to C, but f of x2 is not in my epsilon neighborhood of L. And so because we have we're doing a construction that essentially produces only outliers of our epsilon band, this is going to be how we find that sequence of outputs that is not within epsilon of our limit. Okay, so let's write up our proof. And again, this is by contrapositive. So we're going to assume that the limit as x goes to c of f of x is not L. Then remember what that means. That means that I get an epsilon value such that no matter what delta I pick, there always has to be an x in my domain such that x is in the delta neighborhood, so x minus c is less than delta, but f of x minus L is too far away. It's an outlier. It's greater than or equal to epsilon away from L. Now my goal is to pick a sequence. So let's go back up to this statement. I am trying to prove that there exists this xn that's a sequence in A with xn not C such that xn converges to C. So I'm picking these values, and the way I'm going to pick them is by choosing values of delta and getting their corresponding outlier x. So I come back down and I'm going to say consider delta n equal to 1 over n for each n. By definition, here I'm referring to the definition of the limit not being equal to L, there must exist an xn in A such that 0 is less than xn minus c, which is less than delta, but f of xn minus L has to be greater than or equal to epsilon. Now, I need to prove that xn is converging to C. And then I need to prove that f of xn is not converging to L. So what we have here is we have a sequence of values that we have collected. It is from A. The reason I know xn is not equal to C is because of this strictly greater than 0 part of my inequality. And we also know that xn is going to have to converge to C by the squeeze theorem. Since, remember, the delta n values we picked as a sequence were going to 0. So going back up to our picture, we were saying, all right, pick a first delta value. There it is. Then pick a next delta value that's smaller. So in this case, our first value is 1, our next value is 1/2. And we just keep picking values that are getting closer and closer. And every time we shrink delta, we're getting a new outlier. And in that way, we're squeezing our outlier inputs towards C. So we have that condition, but now what we need to demonstrate is that f of xn does not converge to L. Now, by construction, for this epsilon greater than 0, and for all n in the natural numbers, f of xn minus L is greater than or equal to epsilon. That is, all terms in the sequence of outputs are outliers. Thus, f of xn does not converge to L. So the sequential criterion actually gives us two things. The first thing that it gives us is a divergence criterion. For proving that the limit as x goes to c of f of x does not exist, because it says that if the limit is L, that's equivalent to knowing that every sequence converging toward C has to have outputs converging toward L. So if I can find two different sequences that have different limits, then that's my way of saying that the limit doesn't equal L and in fact just doesn't exist. So I want to find xn and yn that are both sequences in A with xn not equal to C and yn not equal to C. So these are just two different paths of approach. So xn should be going towards C and same with y. But if you look at f of xn, that's going to go to some L1, and f of yn is going to go to some L2, where L1 is not equal to L2. Or alternatively, you could just find one divergent sequence. You could find an xn contained in A with xn not C, such that xn does converge to C, but f of xn diverges. So to see how to use this divergence criterion, we can go back to the example that we looked at in the previous video, where we said we were looking at this step function. So f of x was the function that was 1 when x was greater than or equal to 0, and negative 1 when x was less than 0. And before we just proved that the limit was not equal to 1 as x goes to 0, but now we're able to prove that the limit as x goes to 0 just plain doesn't exist. And the way we do it is using the divergence criterion. We find, so I'm going to draw our picture. So here we have our function. And what we need to do is we need to find two different sequences that converge to different locations in terms of their outputs. So we're going to find two sequences, both as inputs are going to converge, so say this, towards 0. But if I look at their outputs, I'm hoping that they go to different spots. So there's one of my sequences. So this could be my sequence xn. So for example, I need an xn going to 0. That's always from the right. That's 1 over n, for example. So note here, xn doesn't equal 0, which is our C value. But xn does go to 0. And if we look at f of xn as a sequence, that's just a constant sequence, 1, 1, 1. And that converges to 1. Also note that the value that we're selecting for xn is actually a member of the domain of this function, which is all real numbers. So be careful to check your domain. And then I can pick my y sequence to approach 0 from the left-hand side so that my outputs end up on the negative branch of my function. And so I could let yn be the sequence, say, negative 1 over n. It's a member of R. Again, it's valid because it's a path of approach toward 0 that's never actually equal to 0. We see that yn goes to 0. But if you look at f of yn, That's the sequence of outputs, which we are, since we're plugging in negative numbers, all of those go to -1 by definition of our function. And since 1 doesn't equal -1, by the divergence criterion, the limit as x goes to 0 of f of x does not exist. So this is our analog of sort of saying the limit from the left doesn't equal the limit from the right. There's one more thing that the sequential criterion for functional limits gives us, and that's just that we get an ALT for functional limits. And that's just saying that if we know that the limit as x goes to c of f of x is L, and that the limit as x goes to c of g of x is equal to m, then we can do constant multiplication, we can add limits together, we can subtract them, we can multiply, and we can divide, provided that the limit we're dividing by is non-zero. So the first thing we got here is that if I take a constant times f of x, that's just going to be a constant times L for its limit. And this is true for all k in R. And then if I look at the limit of the sum of the functions, that's just going to be the sum of the limits. We also have products. So that should just be the product of the limits. And finally, if I do a quotient, it should be the quotient of the limits, provided that m is not 0. And we actually don't have anything to prove in this theorem, because we can just say, well, if we are given that our limits exist, so that is important, we're given the limits exist, then we can use the sequential characterization to convert these limit definitions into statements about sequences. And we already know that when you have convergent sequences, you get the ALT. And so that gives us all of these, that we can use the ALT to build the sequential characterizations of each of these statements, and then just go back and say, so that means that the limits of the functions have to behave using those same algebraic properties. And that's it for this section.